Okay, so I'm going to review really briefly what we currently know about the impact of low Earth orbiting satellites on the Rubin Observatory and science programs that are going to be pursued by the LSST survey. So it all started with last May with the launch of Starlink, the initial version of 0.9s. They appeared to be about 4.5 to 5th G magnitude. And the initial analysis was that it would create a streak in the LSSTCAM focal plane that was just below saturation, creating some issues, which I'm going to talk about. First, however, we did Peter Yoakum did an interesting simulation where he simulated the number of LEOsats that have been requested by SpaceX for their system, which is around 40,000+ eventually in their build out. And this is a plot showing where how they would appear from Cerro Patron. On the left, you see the Terminator moving in, and the gray is below the horizon. You see there are a few places you might look briefly, but in the next slide, you can see that the problem is that if you try to observe with the current LSST scheduler, that's in the blue with no satellites. That's the distribution in sun altitude during normal observing. But as you get more and more satellites, you begin to lose the number, a large fraction of the successful observations simply because you're trying to dodge them and the whole system chokes. So that's a problem that we're working on, but I'm not too hopeful that we're going to solve the problem for the 107,000 satellites that have been proposed so far, which I'll give a link to in the last slide. So this shows the typical trail on the focal plane of LSSTCAM. It probably would intercept on the order of 15 CCDs or so out of the 189. And so we decided to go into the laboratory and imitate the effect with the simulator that we built, where we have on the right, you see a mask. And in the mask, in this case, was a Starlink slit. And then we illuminated the CCD through the system with a streak that was about the right intensity for what our measurements of the Starlink 0.9 satellites were. And we saw an interesting effect, which was known to exist, mainly that bright objects, including stars, and also including the streak, create a crosstalk between the various between pairs of the 16 segments of the CCDs. And this is due to the video signal on the output coupling to other output video signals. There's 16 video signals out of each CCD. And the origin of this is interesting. We don't fully understand it, but the issue is how can we correct for it? That's the first issue. The second is, of course, the trail itself, which I'll get to. So this is called crosstalk. And one of the things we found, unfortunately, is that the crosstalk is actually nonlinear. It would be expected to be linear if it was just capacitive coupling in the cables, but here Andrew Bradshaw has done an analysis showing that the crosstalk actually between pairs of channels, and this is just the positive crosstalk, there's also negative crosstalk, is nonlinear. If it were linear, the way this data is reduced, the graph should be a horizontal line. And so it's nonlinear on scales that we have to correct for. But we know that we can measure this only to a certain accuracy. Therefore, if we want to correct for the crosstalk down to way below the sky noise level, this implies a maximum brightness for the trail itself. And so here you see his simulation of a faint trail now from a satellite that would appear to be around 7th magnitude or so, not 4.5. And you see that his algorithm is able to correct for the first and second order crosstalk signals. So this set a limit to the apparent magnitude of the satellite at any time. So we reached out to SpaceX and have been working with them on this. More on that in a minute. But this plot by Beaujean shows the situation vertically. It's the pixel count in electrons, so that's a kind of a surface brightness. And on the x-axis, the satellite apparent magnitude if you were tracking it. And the points are various different of our 6 bands. And this is for a group of satellites at 550 kilometers, which is the SpaceX Starlink satellites. And because they're slightly out of focus, because the mirror is large and we're focused at infinity, it actually spreads the light out a little bit. So the trail full width is about 2.5 or 3 arc seconds wide. And that range of correctable crosstalk was what I was referring to. Mainly there's a capture range, a sort of dynamic range where with the precision that we figured that we can measure the crosstalk in each of the 189 times 16 crosstalk matrix elements, we can correct it down to a fraction of the sky noise only for satellites which are sort of in that general range, sort of fuzzy. But as you get fainter than 6, maybe to 7th magnitude, it starts getting possible to do. And so that gave rise to the 7th magnitude number that we went and gave to SpaceX as a goal. So they started playing around with various ways of darkening the satellites. This is known as DarkSat, where they went in and, as you could see, darkened 4 of the 10 gigahertz phased arrays, which were effectively white Lambertian reflectors of the sunlight. And indeed, it did darken it. This is their first experiment. And Tim Abbott and Meredith Rawls are responsible for what you're looking at here. This is CTIO Blanco decam image where a series of images where they caught 5 of the satellites, and the 4 up there at the top are around 5.2, a little bit brighter magnitude. Those are undarkened version 0.9s. And down below, satellite 1130 is DarkSat. And so they by doing that, they made it about a magnitude painter. That's probably not good enough, but they're working on it. There's something called VisorSat, which has been launched and will reach orbit maybe in another operational orbit in another few weeks, and we'll be able to maybe look at it this fall. So SpaceX is working with us to address the mitigation. There are a lot of things that we're jointly trying to do. One of them is to make the Starlinks about 10 times darker than the V.9s. And if they do that, it'll, as I mentioned, will remove some of the trail artifacts, such as the nonlinear crosstalk, or at least we can process the data to eliminate that. However, even if we're able to do all of this, the main trail still exists at a very high signal to noise ratio. The trail is quite bright, probably around 10,000 to 20,000 electrons per pixel. This complicates the data analysis, actually the whole process of data processing, but particularly the science analysis, and will limit discoveries. So here we have a case where we found something quite like this on Subaru. This is the Fuse 1 satellite, which is about the same altitude, about the same range, and the same brightness generally as the version 0.9s. And this is a piece of a CCD on the Subaru image. And in the next slide, you can see a problem, one of the many problems with this, and that is that if you take a look at the surface brightness plot across the trail, down at the bottom is a log plot, you can see that actually at surface brightnesses that could affect some of the science cases in the LSST, the trail is actually quite broad. It's around 10 to 15 arc seconds half width. So it's 30 arc seconds wide. And this can create a broader swath of impacted pixels. And we may or may not be able to mask them in a way that would get rid of the remaining artifacts. So since LSST, the survey is going to be limited by systematics rather than the usual statistical effects from sample size, we care about systematics. So this is a new paradigm, of course, the systematics limited science, with tens of thousands, now 100,000, have been applied for. Generally, we find that there's no combination of mitigations that can completely avoid the impacts of the satellite trails on the Rubin Observatory science programs. Because we're designed to probe the dark sky in new and dynamic ways at very low signal noise and to unprecedented faintness. So that we do have a problem that we're trying to address by working together with the operators. At the end, one of the science applications of LSST is indeed to discover the unexpected. The dark sky holds secrets that have not been probed yet. And one of the things that we all expect LSST to reveal is something new. So the next steps are to continue to work with industry, actually all the operators, to develop darkening and joint operation solutions to minimize the science impact. A couple of examples are tools for efficient scheduling. And then very interestingly, we think we can probably get predictive luminosity models where each satellite will have some kind of advanced prediction with regard to its apparent brightness as a function of time as it scans across the sky over your observatory. We're working together to develop observing strategies and new data analysis methods to partially correct for these effects. And then I think the thing the real homework assignment we have, which we haven't fully started yet, are to explore through simulations the science impacts on the LSST. So this is where you can find some more information. There is a paper that's given there on it. There's a workshop that we had very recently called SatCon 1, and you can download the presentations. We're coming up with a report to the NSF and DOE shortly as a result of that. And then there's a very scary movie that you can look at, which is that last link there that was made showing the progressive effects of these satellites as a function of time over the next decade. Thanks.